Good evening. My name is Todd Urbach. I'm a board member. I guess I will continue to be a board member, thanks to all of you, until Heather kicks me out. And I'm with the program committee. So, as if ice cream wasn't enough, you're in for another treat. Tonight is the last lecture of our Made in New Mexico series. Now, I cut this out about a year ago in anticipation tonight. Can everybody see that?
Pearls before swine.
I don't know if I can read it. Hold on.
What's the matter?
All right. First frame. What's the matter, Steph? This company is offering to beam any message you want to Mars, but I only have till November to give it to them. Everybody starts yelling in his ear. Write something profound, something eternal, something brilliant, something deep. Think Shakespearean, Plato, Einstein, Da Vinci. Right. I like beer. That's our message to Mars. Rush me. Mars will be so impressed. All right, so I've been sitting on that for a long time. I almost forgot.
Our local beer.
That's not. Okay. Next year, our lecture series will commemorate the 70th anniversary of the end of World War II. In August, so put this on your calendar, we normally don't start till September, but in August we'll have a special lecture by New Mexico State historian Rick Hendricks. Okay, so everyone come out for that. It's on the normal second Tuesday of August. Huh? The role that New Mexico played in World War II, the end of World War II. Okay, who's the newest Los Alamos Historical Society member here? Raise your hand. I really thought it was going to be easier than that. All right, I want to thank all the sponsors of this lecture series. First of all, the members of the Los Alamos Historical Society. Everyone give yourselves a hand. These lectures, I think, are really impressive. So, and I want to thank you all for coming out and spread the word, get more people out to these things. The Los Alamos National Bank sponsors this lecture series. So, if you've got some spare dollars, give some to the Historical Society, and deposit the rest with LA&D. Now, last month, who was here when President Truman arrived for the lecture? Now, I neglected last month to mention that President Truman was sponsored that night by the New Mexico Humanities Council. Okay. I forgot to warn you, but tonight's introduction won't be that long and drawn out. All right, so like I said, we have a treat tonight. Nina Lanza is here with us tonight. She's a scientist at the Los Alamos National Laboratory. She is living her dream of working on a spaceship with lasers on Mars as part of the ChemCam instrument team on the Curiosity Rover. Nina is broadly interested in understanding the history of water on the Martian surface at a variety of scales. Her most recent work focuses on manganese in the Martian environment and its implications for habitability. Nina was born and raised in Boston, Massachusetts, and was educated at Smith College, where she got a BA in astronomy, Wesleyan University, where she got an MA in Earth and Environmental Sciences, and the University of New Mexico, where she got a PhD in Earth and Planetary Sciences. She became enamored with space exploration after seeing Halley's Comet in 1986 and has pursued work in the field ever since. Now you might wonder, how did Dr. Lanza get into Mars? Well, she had a professor who asked, well, what would you be doing or studying if no one was forcing you to do it? And she made a list of 3 items. Number 1, spaceships. Number 2, aliens. Number 3, science fiction. And there you have it, Mars. Dr. Lanza is married to Mauser Williams, whom I'm assuming some of you know. And he had her father as a professor. And they were married during the launch of MSL that carried the Mars Curiosity Rover, which is really cool. So, everyone, let's give a big round of applause to Dr. Nina Lanza.
Thank you. Hello, we got a little feedback. Can you hear me? Okay. Thank you so much for this great opportunity to speak to you all and a great introduction. I am so excited to talk to you about Mars, which is my second favorite planet. So I'll just start by showing this is a new picture that we just got. It's a little hard to see what this is, but these are actually veins, really big veins sticking out of a rock. And this is really, this happens on Earth when you have waters flowing through rocks. So this is a really great indicator of habitability. And we'll talk a little bit more about what that means, but I just wanted to show you some of the new stuff. So just a little bit about this rover. Its official name is the Mars Science Laboratory, or MSL. It's actually been dubbed Curiosity by students. We have a contest for all of our rovers to be named by students. So you can see it's not the first rover we've sent to Mars. So this is an image taken at the Jet Propulsion Laboratory in Pasadena, California, at our Mars yard. So this is where we test rovers. So these are two full-size engineers here for scale. So you can see we've actually sent some other missions to the surface of Mars. Right here is the Pathfinder mission, the little Sojourner rover that we launched in 1996. And then a little bit after that, you may recall the twin Spirit and Opportunity rovers that we launched in 2003, a little bit bigger. And finally, in comparison, this is the Curiosity rover, which is enormous. It really is the size of a car. And we call it the Mars Science Laboratory because it has 10 different instruments on it. It's really an incredibly capable rover. It's like sending a miniature laboratory to Mars. So we can actually do quite a bit with this rover. So we wanted to send Curiosity to Mars to assess the past and present habitability of the Martian environment. So this is not a search for life, but rather places where life as we understand it could exist. So there are some criteria we can look for. There are things that all life as we understand it need. Water is a really important one for that, right? We need to find water. But it doesn't just need to be in a liquid form or even in ice. It can be bound up in minerals. So we can also look for hydrated materials or materials that only form in water because that tells us how much water was there in the past. We're also looking for organic materials because those are the building blocks of life. And we're also assessing the surface radiation environment. And this is actually not only to understand habitability, but also in preparation for a future human mission to Mars, which we're hoping will be in the 2030s, fingers crossed. So this is one of my favorite pictures we've ever taken. This is a selfie that the rover took on Mars. So it actually has an arm. A lot of people say, oh, where's the arm? This is Photoshop, there's no arm. But remember, when you take a picture of yourself with your phone, most of your arm is not in there. So the arm would be coming out here. And so that looks like, this is the end of the arm that has instruments on it. But this is actually Curiosity sitting on Mars. And you can see this is this big mountain in the background. And this picture was so beautiful, actually, that we made the cover of Science, which was pretty exciting. Yeah, this is our cover girl. So as I said, there are a lot of instruments on this rover. So I'm pointing out all of them. But I do have one favorite. It's the one that I work on, and that's this one up here on the mast called ChemCam. It's a chemistry instrument. You can see this is what it looks like outside of its housing. So I'll tell you a little bit more about this one in particular, just because that's the one that we work on here in Los Alamos. But it's actually not our only contribution. So I know the theme of your lectures have been made in New Mexico, but there's quite a bit on this rover that has been made in New Mexico. So here I'm just showing some of the involvement that we've had. So of course, ChemCam here, we have this mast unit and also spectrometers in the body here. We also have another instrument that's called ChemIn. It's our sister instrument. It's an X-ray diffraction instrument. So the deputy PI was here at Los Alamos. And we also power the rover. This rover is entirely nuclear powered. It has no solar panels because it's so big and powerful. Solar panels would just not be enough. So we made the plutonium. And so that's also here. So that's right here in the back, which you can't see. But so yeah, we had a lot of parts of New Mexico are actually on Mars right now. So I'll just tell you a little bit more about ChemCam. I'm sure many of you already know a lot of this. This might be review, but if you haven't. So ChemCam is short for chemistry and camera. So as you might imagine, there are actually two instruments in one. The first instrument is the laser part of this. It's a technique called laser-induced breakdown spectroscopy, or LIBS. And this gives us chemistry data. And we can actually sample a target up to 7 meters, or about 23 feet away from the rover. So you can see this is an artist's conception of what that looks like. So we can actually shoot something that we couldn't drive up to. And we also have, along with this laser instrument that can get chemistry, we have a remote microimager, which is a camera. So we actually take an image of where we shot with the laser so we can get a geologic context for that chemistry information. So you can see this is sort of, we get two data products back. We get this a spectrum. So this is wavelength along the x-axis. This is the color of light. And this is the intensity. So you can see we actually see spikes. So the way this works is we actually excite the target atoms, we vaporize it with this laser. And as these target materials are coming down from their excited state, they actually will emit photons at a particular wavelength. So really, we're looking at the color of light that comes back, and we can tell what we actually shot, what the elements are in the target. So that's what our spectrograph shows us. And then we also have an image here. And this is a picture of a rock that we named Harrison that we saw on Sol 514. That's 514 Martian days into the mission. And you can see we see individual mineral grains here. My laser here is not working as well as ChemCam, unfortunately. So you can see that, we can see where we shot. We shot on this white part, this dark part, and we can see that there are chemical differences between them. And that really helped us understand the geology with this instrument. It's a great instrument for this. So it has a really small spot size. We really can see these little grains. It's about 0.5 millimeter in diameter, depending on how far away we are from the target. And we can actually do a depth profile, so we can pulse the laser multiple times and get composition. We vaporize a little bit and vaporize a little bit more, and then we can actually get a depth profile of composition into the surface. So that means we can also clean off the surface with, if there's dust on it, and we can see how that composition changes. Oh, I've been told I need to move one of my many microphones. Let's see. One moment here. It's glued on. Okay, is that better? Okay, thank you. We'll see how that goes. So this is actually, this instrument is not just built by us at Lanza. It's actually a collaboration between the US and the French Space Agency. So this is a picture of our team taken in France in 2013. And we were actually at the Cité de l'Espace, which is one of their museums that they have at the Space Agency. And you can see there's actually a full-size rover right there in the background. But we are so many of us that we basically block it. But at least you can see ChemCam right here. So I'll tell you a little bit about now where we landed on Mars and why we wanted to land there. So we went to a place called Gale Crater. I put a box around it here. You can see it's right here. But I've also labeled some of the other landing sites that you might be familiar with. So Spirit is right here, kind of our neighbor. And Opportunity is here. The Phoenix Lander is here. Here's some of the Vikings. So this, I haven't actually put a scale on here because I'm a bad geologist, but just to show you, this is Valles Marineris, which is a very big valley. That's the width of the United States. So just to give you a sense of the scale. And what you're looking at here, the colors here are representing elevation. So the higher the elevation, the warmer the color. And the cooler the color, the lower the elevation. So you can see right here, we're actually on this boundary. There's a boundary here where in the northern hemisphere, there aren't many craters, and it's actually very low. Whereas in the southern hemisphere, there are a lot of craters, and it's actually much higher. Oh, and this, just so you know, this is Olympus Mons. This is the largest volcano in the solar system. Put this on top of the United States. That's terrifying. It's quite large. So you might wonder, okay, so why is there a difference between the northern hemisphere and the southern hemisphere? In planetary science, we can do relative dating of surfaces by looking at how many craters are still on the surface, so how big they are and how many there are. And that's just because there's not as many processes on Mars removing the surface, recycling the surface materials as there are on the Earth. The Earth has had many impacts as well, but we don't really see evidence of them because they have been eroded away by our water cycle. And Mars hasn't had as an active water cycle, so we still see a lot of craters, but not here. So one of the leading hypotheses why we have this really low-lying flat area is that there was actually a hemispheric ocean. This whole area was an ocean sometime in the past. And that's why it's such a young surface compared to this older material here. So we decided to go to Gale Crater because this is right on this edge of this dichotomy between younger and older materials. So this might be a great place to get a broad swath of geologic time represented in the materials that we see. So I'm going to zoom in a little bit on Gale. So it's a crater that's about 150 kilometers in diameter, so about 100 miles in diameter. And the really interesting thing about it is that it's filled with this sedimentary mountain, this huge mountain. Woo! I'm blocking this feedback hopefully this way. So this mountain is called Mount Sharp. And it is a huge mountain. It's the size of Kilimanjaro in Africa. So that's the tallest mountain in Africa. It's over 19,000 feet tall. So that's such a large mountain that it's actually taller than the edge of the crater. So that's one of the clues that tells us this is something that is sedimentary. And indeed, when we look at orbital data that we have from our orbiting spacecraft, we can see there are minerals in there that seem to be water-formed, things like sulfates and clay minerals. So this seems like a really great place to start looking for habitability. This is a place that seemed to have had water there in the past. So when you look a little closer at our landing site, we actually landed right on this alluvial fan. So we had, it looks like a stream depositing materials down here. This is the mountain here. So that's why we decided to go there, because our mission was to assess habitability. So this seemed like a place that might have been habitable, at least in the past. So just to show you what this looks like, this is actually a picture taken by the rover of Mount Sharp. You can see it kind of looks like the Grand Canyon, right? It looks very terrestrial. It's very familiar to us. These are these sedimentary layers that we can see that have all these different water-formed minerals in them. And so in geology, when you have layers like this, frequently it tells you a story of how one material moved to another. So older materials are going to be emplaced first, and then younger materials on top. So as we drive up this mountain, we're actually going forward in time. We're starting back in time, and we're learning about the history of this area through the rock record. And just to give you a sense of scale, I put a box around here of a boulder that's like 5 pixels wide here. That's actually the size of the rover, so that's, you know, a car. So it's actually a really huge mountain. And we are not yet anywhere near this, although we're making progress. But this is where we're heading. So, I was going to now show you a video. So we had a really exciting landing mechanism, or terrifying, depending on your point of view, because you can't test these things out. So I'm going to show you an animation of what it was supposed to do, and then I'll show you a video from the rover, the actual video of its landing, so you can see what it did. And just spoiler, we totally made it. Okay, here we are. We just launched from Florida. So now we got rid of our big fuel tank here, and now we're heading to Mars. Fast forward now 8.5 months, we made it to Mars. So while as we're heading into the atmosphere, you can see there's these little rockets firing. This is actually steering the spacecraft. This is the first time we haven't had a ballistic landing, so we could actually steer it a little bit better. So it's not just falling. So it's also going to be, so it's braking in the atmosphere. The atmosphere is a lot less dense, so that's not going to be enough. So now we pop out a parachute. But again, Mars's atmosphere is not that dense. So this is where the video is going to start. We pop off the back shell, and now the rover can actually see the surface. This is the crazy part. This is a sky crane. So this is supposed to gently, slowly lower the rover down on this cable, right? Very gently, very slowly. And then it's going to detach itself, and it's going to fly somewhere else to die, not on top of the rover. So that's the plan, right? So this is not tested. It's not testable. So the first time we tried it was landing night, which was August 5th, 2012. So you might be able to hear some of the audio. This is from the entry, descent, and landing team. Oh, sure. Okay, so you can see, so here are these dark sand dunes. There's some mountains. The mountains up here, that back shell just popped up, but we're still actually quite high. Okay, so now we're a little bit closer. People are cheering because we're getting the telemetry that says we have not crashed and died yet. But of course, that's 7 minutes delayed, so we don't know that this has happened until it's happened. So it's a little hard to see scale here, but once we're about 5 meters up, you'll be able to see a huge plume of dust from the sky crane, because Mars is a very dusty planet. So we're getting a little bit closer. And eventually, you'll see, so we pick up this huge cloud of dust. It's actually going to be very dark in the image. So you can see now we're very close. So much dust is going to be kicked up, it's actually going to become very dark. So there's the wheel, so that's good. We unfolded the wheel, which means we're not going to be a lander, we're going to be a rover. That's a good thing. So, so we're all in the basement at JPL, and we're just like really hoping that this does not crash so we don't have to find new jobs. It's a little bit terrifying. You can see it's okay, it's really dark here, it's really hard to see what's happening. But now the dust is clearing. Look, these are pebbles. That's the first ray of sunshine under our rover. And that's the first picture we had from Mars. So eventually, 7 minutes later, we got this picture, and we were pretty excited. I think you just heard one of the EDL people. These people just went crazy. This is our entry, descent, and landing team. They were pretty excited. People ask me, like, if I had a blue shirt and I was in that room. The answer is no. That was for the engineers. The scientists are less photogenic. We were in the basement, but we were doing the same thing. So we landed. So then we actually had to get to work that very evening because we're on Mars. So here's just an image of where we landed. Look at this beautiful vista. There's, Mount Sharp, size of Kilimanjaro in the background. There's those dark sand dunes that you could see from as we were landing. And you can see, Mars is pretty red. It's the red planet. But right here, this is one of those scour marks from the retro rockets. So we blew a lot of dust away from there. And we're like, well, that's interesting. Mars isn't very red under there. I wonder what that stuff is. So we took a little drive over there, and this is what we saw. So at first, I know, when you see this picture, you're like, oh, it's a piece of cement. That's not exciting. But this is on Mars. So what this is actually a rock called a conglomerate. That's a rock that's made up of other rocks. And so the way it forms on the Earth is that you have flowing water over a long period of time, and it's moving pebbles and smoothing them out, and eventually that water is going to evaporate, and it's going to cement those rocks together. And so I actually have an example of this is a conglomerate rock from Earth. This is one I collected myself in Utah. And you can see it's very, very similar in character. So this is really a textbook example of a conglomerate. So this is immediate proof that we've landed in a place that had persistent flowing water. And that was just right at our landing site. So this is definitely a place, definitely a place that was a habitable environment for sure. And it was amazing to have landed on it. So I'll tell you now, I'm going to walk you through some of the other results that we've had since then. So we've been on the planet for almost 3 Earth years now. That's 1.5 Mars years. So we also found that there were quite a bit of clay minerals, a variety of clay minerals in this location. So we knew that there were some clays from orbit. We really confirmed what kind they were. And so clays typically form in water-rich environments. And the type of clay that we found is a smectite for you geologists out there. So it's very common on the Earth. And again, very telling for the type of environment. So we drilled. We have a little drill on the arm. It's actually a percussion drill. This is an image we took of it with the ChemCam imager. So it's a percussion drill. It doesn't take a core. So here's a before and after blink image. And so it's not a very big hole that we're making. So you can see it's about the size of a US dime. So it's about 18 millimeters in diameter. You can see as we drill, again, Mars is not very red under there. It's actually very gray, which is very telling because the dust is the part that is really oxidized in this location. And not the rock underneath. So this tells us that there was actually water, a lot of water here, and not just any water, but water with a relatively neutral pH. It wasn't very acidic and it wasn't very basic. It's some water that you could drink. So yeah, very exciting result, and that's actually the first time we've really seen such strong evidence of neutral waters on Mars. Here's an image that we also took with ChemCam. And it's been colorized with the mass cam. So this is the drill hole, and you can see these little red marks. Hard to see here, but these are little shots. So you can see we burned little holes in there. So we did an analysis of those materials. So you can't escape from a ChemCam talk without seeing one spectrum. I'm sorry, I have to show you. But this is actually pretty exciting. This is the very first spectrum we ever got from ChemCam. And so we got this on Sol 14. So that's 14 Martian days into the mission. This corresponds to my terrestrial birthday, so it's great, a great present. And so I worked with this instrument. I worked with the instrument before it was sent to Mars, and it had really beautiful spectra. But we never saw anything as beautiful as this. This is even better. And it was like shaking the optics somehow made it better. That almost never works, if you shake your optics. It doesn't get better, except in this case, which was great. So I'm showing now so we have wavelength along the x-axis, so that's the color of light. This is in the ultraviolet. This is sort of the blue-green, and this is the red and near-infrared. And so I've labeled some of the elements here, but I want to draw your attention to a very small peak, but very important peak, here at 656 nanometers. This is actually, so I'm showing you an average of 50 shots here, 50 pulses with the laser. This is now showing individual shots, and you can see our very first shot, we have a really big peak of hydrogen. And that was really interesting to us, because that tells us immediately that this is hydrated material. And it turns out all the dust on Mars is hydrated. All the dust actually holds onto water or hydroxyl, which is OH. And that actually answered a long-standing question that we had about Mars. We had seen with other instruments, we had seen a signature of hydrated materials, but we didn't know what it was in because we looked, it didn't seem to correspond necessarily with the terrain. But it was the dust, and the dust is everywhere. The dust is ubiquitous. So that was one of our very first and major results that we had on this rock that we called Coronation. This is the picture of it right here. So it's just a dusty little rock here. But it was so exciting to see this. And it gave us a great spectrum. We were off to a great start. So another result that I'd like to tell you about, this is a little more new. This is something we just released in December. We actually found methane in the Martian atmosphere. And not just any methane, but actually methane that has variation. So it's not consistent. It doesn't seem to have a pattern that's, changes with the day or even the season. It actually seems to be little puffs of methane coming from somewhere. Now this is really interesting because methane does not last in the atmosphere. It breaks down relatively quickly. So, on the order of tens of years, maybe 100 years max that it could last. So something is making methane on Mars right now. And yeah, we don't know what that is yet. There are a lot of options. It could certainly be a volcanic product. It could be some little outgassing from fractures. But what's really interesting, of course, is that methane is also a product of metabolism. So microbes can make methane as well. So of course, we don't know which one this is. We don't know where this methane is coming from, but we know it's happening right now. And so that's really exciting for us, for all of us. So I think at the very least, it provides organic carbon for life to use. So this is something that we just released hot off the presses. And so now I'm going to tell you about my research because I can't help it. It may seem a little less exciting, but hopefully I can explain to you why manganese is so awesome. So one of the other things that we found was the very high concentrations of the element manganese. So that's a transition metal. It's in between chromium and iron on the periodic table. And so this is where we found it, actually. This is another selfie the rover took, and I love it, too, because it's looking at my favorite rock. I wrote a whole paper on this little area right here, right there. So it's great. I'm this is the most important thing Curiosity is looking at. And it's an area called the Kimberley, named after a place in Australia. So what this tells us, I'll give you the summary first before I go through it, but it's high concentration of manganese tells us a lot about the aqueous environment. So it has to be very oxidizing, and it also has to have a lot of water, so very wet. So these are things we know from seeing manganese on Earth. So these are the places where we tend to see high concentrations of manganese on Earth. Okay, so we see hydrothermal systems, deep sea nodules, rock varnish, and some fracture fills. So all of these places, even in the deserts on the Earth, there's quite a bit of water that is helping to form these materials. So to do this, as I said, you need liquid water, and you also need these strongly oxidizing environments. So what do I mean by oxidizing? Is actually having oxygen in the atmosphere allows us to deposit manganese now. There's actually a really strong association between manganese concentrations and biological activity on the Earth. We don't actually see manganese deposits in the rock record prior to the rise of photosynthesis, so before we have an oxygenated atmosphere. So when we find something like this on Mars, it opens up the question, did Mars have oxygen in its atmosphere at some point in time? And if so, how did that happen? I mean, we have no idea. That's not something we ever thought was true about Mars. So this is, again, we're still investigating in this, but this is ongoing work, and so that's what I'm doing. So now if somebody asks you about manganese, you can be like, that's the greatest element. So that actually was found at this place called the Kimberley. So I thought I'd just show you. This is an image taken by an orbiter called HiRISE. So this is the rover, actually, standing by that outcrop right there. You can actually see our little rover tracks, driving up to it. But yeah, we actually follow. I'll talk about this a little bit more. We actually do track the rover with our orbiting spacecraft. But you might, it's super cool. So you might notice there's actually these sort of striated materials, sort of bright material here. And we actually saw that all over Gale when we started looking carefully, and we weren't really sure what we were looking at from orbit when we were doing mapping before we landed. But now that we're there, we can actually take a look at it. So it looks like this when you're right up against it. And so you can see this is actually a sedimentary material with some layers. This is equivalent to something like a sandstone or a mudstone. And it turns out all these beds are dipping in the same direction throughout the location where we've traversed. And we've had the opportunity over these last 3 years to map that, and we think we actually understand how they formed. So this is actually really a diagnostic type of deposit that's formed by deltas. So when you have a stream hitting a body of water that is not moving, so that would look something like this. This is just a little cartoon of that. So you have rivers coming in, hitting this water of a lake, and then forming these deposits, which actually you're slowing the water down and making it drop its sediment out. And so that's how we form those kind of rocks on the Earth. So that's just another piece of evidence that says that this whole region in Gale Crater was filled with water and had a long history of having a habitable environment. So that, just to show you what that kind of looks like, this is an artist's conception. This is the crater again, this Gale Crater with the mound here. This is where we started, and here's where we think the lake was. We think there was a lake that filled this whole area, and those are all the minerals, so we've been traversing along here, and we're actually right about here now. So we kind of left the lake bed and are moving now up the mound right now. But so that's what we found in the last 3 years, and I think, well, we're just starting really, but that's a lot to learn. So I thought I'll now show you some of the other cool data that we've taken, now that you know the full story of Gale as we know it. I really love this picture. So in the fall of last year, we actually had a really close approach of a comet to Mars, the comet Siding Spring. So this is an image taken by Hubble, and I know it looks fake, but this is a real image. This is Mars, and this is that comet. And it was really close. It was only 140,000 kilometers, which does sound far, but that's actually only 1/3 the distance between the Earth and the Moon. That's a very close approach. So of course we tried to take advantage of the fact that we have all these instruments there. So we made observations by 10 different instruments from 5 different Mars missions. So there's quite a bit of data that we took on this comet just because it happened to be there. So I thought I'd show you a little bit of what this looks like. So of course our instruments are not optimized for looking at the sky, but this is an image, these are a series of images taken by the Mastcam. So it's hard to see, this is a star. This is the comet. So we can see it's moving here. So we took it over a series of days, so there's 10 different exposures. So that's the comet being observed by a spaceship on Mars. Pretty awesome. So this is a very new piece of data. This is a series of images. This is the first color sunset we actually took on Mars, and this was just taken on Sol 956, or for terrestrial people, the 15th of April this year. And so you can see that it doesn't really look like it's the sunset, right? It's not red, but that's just because Mars does not have as thick an atmosphere, and it also has a lot of very, very fine dust in the atmosphere, much finer than what you find on the Earth. So you're actually scattering the light in the blue as opposed to red. So that's why the sunsets on Mars are a little bit blue. And so that's what it looks like from where we are approximately. We just moved like maybe 50 meters or something like that, so we're right around there. So then I thought I would tell you a little bit maybe about something you might have heard of. You might have heard that we had some issues with our wheels. We were making some holes. This is one of the challenges that Mars throws at us, because even though we've been there quite a bit and we know a lot about it, it's still, we don't know everything. If we had only visited 5 places on the Earth, what would we know? So this is a new challenge that Mars has given us. We didn't notice this at first, but we started seeing in our images, like, wow, there's some holes that we did not put ourselves in the wheels, and what is going on with that? Turns out this is what's going on. So this is an image the rover actually took with its arm underneath the undercarriage. This is the rear wheel. It's actually balancing on this rock. The rover is being held up by this pointy rock. That's a really pointy rock. So that's how we're poking holes in our wheels, is from these very sharp rocks. And you might wonder, well, didn't you guys know that rocks were pointy and sharp? And we did, but we didn't know that they were this hard. So rocks like that, we call them ventifacts. So these are wind-eroded rocks. They're scoured, and they can be very sharp. So I found this picture online. I liked it a lot. This person is showing, this is like a blade of a rock. This is a ventifact on Earth. This person is pushing down on the rock, and you can see it's actually so sharp it's indenting his fingers. So these are really sharp rocks. The wind can actually really affect, they can really sculpt rocks over a long period of time. So we just didn't know. I mean, we've been to Mars before, but the materials at Gale are just harder than the other landing sites. We just didn't know. And we're using what's called a rocker bogie system, this is suspension, which keeps the body of the rover from tilting too much. There's not a lot of pitch. It keeps it even. But the problem that you have is that there's actually a lot of load on the front wheels in particular. It's like it's being almost like pulled over. And so so we have the greatest load sort of on the front wheels. And our wheels are actually not made of what the rest of the rover is made of. The rest of the rover is made of titanium, but the wheels are made of aluminum. And that's just, people say, well, why didn't you use titanium? It's because titanium is very expensive and the rover is very large. And so we didn't think we needed to have wheels that were made of titanium. So we used aluminum because they have worked in the past. We were sort of sad to see that they were not working now. It's not a huge deal that we're making holes in the wheel. We could probably drive if the wheels were square, but it's better to conserve it as a resource. So we have a few solutions. For a while, we decided to drive backwards because then we could put the wear on the rear wheels and sort of spread it out. And then we also now plan our traverse to avoid sharp areas. So now we have a better sense of what the sharp terrains look like from orbit based on what we've seen on the ground. So that's what we're doing. Right now, we're planning our traverse not to drive over these terrains, not because it's going to ruin the mission, but just because we want to make sure these wheels last as long as we need them to last. But as what we learned from this really is, again, you can't really easily predict Martian environments. You think you know something about it, and then Mars throws something new at you, and that's why we're discovering things like this all the time. So I'm showing you this picture again because I love it. But you can see, we didn't just drive here, right? Look at all these sharp rocks. We just drove around, and you can see it. There's sand here, right? So that's why you can see the trail. So that's how we drive now. When we have a goal we want to get to, we find the softest path there. So speaking of driving the rover, you might wonder, how do you do that? I was hoping that there'd be like this big captain's wheel somewhere. You get to stand there. But there is not, unfortunately. It is from our laptops in our local operations center. So this is just a picture of our operations center, which is downtown. It requires a lot of different people, so it's not just one person or two people. It's more like 100 people per sol, per Martian day of planning. So a lot of work goes into that. So I'm going to just tell you a little bit about how that works. So I just want to point out that we did the first 90 sols, so it's the first 3 months, at JPL in California. We all had to move to LA, and we had to live on Mars time. So Mars time, the Mars day, a sol is 24 hours and 38 minutes long, which is just different enough from the Earth day that it really messes with you. So if one day you start at 7 a.m. California time, the next day you're starting at 7:38, so on and so forth. So it's like 1 in the morning, 3 in the morning, and our landing site corresponded to like Mars and California were totally out of phase. So I never saw the sun anymore. But that was a very exciting experience. So the way it worked, we did this in person for the first 90 sols. We do this essentially the same meeting schedule that we have, but we now do it all over the phone. So we plan long-term goals well in advance. So we know that we want to get to this certain mountain or this certain butte, whatever, by some time. So we have to be sure to drive to get there. But day to day, sol to sol, we can plan to do whatever science we want. So people like me can just call up and say, I think we should shoot this rock. And if I can make a good argument for that, then we get to do it. So I just have to convince my 400 other scientists that this is what we should do. But I've been able to do it before. So then when we know what we're going to target, we write spacecraft commands for the rover. And then you might say, oh, we're done, right? We're done. It's not even lunch. But we actually have to check and recheck those over and over again, because nobody wants to typo the commands sent to Mars. So, chances are the rover has software that prevents it from doing serious damage to itself, but you still don't want to waste time, because at the best, you could miss the target you wanted to get. The worst, you could delay the progress of the rover. So we have a lot of meetings to check over that work. And one of the best parts of the day is really our science discussion. And this is when we get to start talking about the data that we've seen and what do we think it means, and we get to throw out our crazy ideas and see, what do you guys think about this? So that's really like my favorite part of the operations, is just talking about what we've seen, because that's why we're there. So I thought I'd just show you some pictures of what this looked like. This is actually a picture at JPL. So this is one of the first meetings of the sol. In the morning, I think this was taken at like midnight or something. So all the instruments had their own assigned seats, only 2 seats. You have to speak into a microphone because there are a lot of people who cannot fit into the room. So even if you're talking to somebody next to you, is it talking to a microphone, which is a little awkward. You can see that ChemCam is a big team, so our seats are here. See, there's like 5 people jammed into this corner because our team is really big, but we only get 2 seats. So I spent a lot of time in this little corner here. This is where the management is, so they can watch us. So we're far away. That's good. So, as I said, so the schedule is a little unrelenting. Like, I felt like really excited about living on Mars time, but I just am really terrestrial, it turns out. We're really tied to the diurnal cycle on the Earth. At least I am. So I got really tired. So this is actually me going under the desk in our little operations room for a nap. This was taken by one of my French colleagues. He put my badge here, so you know it's me. No mistaking it, definitely me. This is hilarious. This was around 5 in the morning, and we had another meeting starting at 7. I'm like, I'm not gonna make it, so I just needed to get a little sleep, and then I could roll in and finish it up. But it's not all toil, because the project gives us free ice cream. So like no one told me this, and like these ice creams would be appearing. I'm like, where is this coming from? It comes from the 6th floor kitchenette, and they give 1 ice cream per team member per stall, and they refill it only once a week. So if you eat all the ice cream before then somebody doesn't get their ice cream. And this shows you, I think they're eating more than their fair share, because this was not anywhere close to the Wednesday fill up. And I never got a drumstick, never. People would just like wait for it. So yeah, so after that picture, when I took the nap and I had to go in for my my 7 a.m. meeting, this is what I rolled in here, got a little cup of chocolate ice cream, breakfast of champions, and I was all set. So when you are not sleeping a lot and you're at work all the time, you go a little crazy. So this is our operations room. We had our very own ChemCam ops. And this is the REMS operations center, so that's another instrument. So our instrument is part French. REMS is a Spanish instrument. So somebody, several weeks in, hilarious, we were very serious at first, and then we stopped sleeping. Somebody put a sign up. The sign says the Pyrenees. And so that actually, yes, for those who don't know, that's the mountain range that separates France from Spain. So then that like opened the floodgates. So like over here, pictures of like Spanish wines and like bullfights and all this stuff. And then the French weren't going to be outdone. So then they were like putting all these pictures of like, French wines, which are clearly superior. And I was like, we're not going to be left out. So I put the Rockies down here. These are the Rockies. Here's the isotopes. I put it down. Some red chili. So we were not left out. Don't worry. But you've probably seen, this is our first spectrum, the one I showed you. We taped it on a door so everyone had to like duck down beneath our awesome spectrum to get into the ops room. But you can probably see there's some other things here that aren't as clear, like what are these things? So when you're exhausted and with your coworkers all the time, you sometimes want to like Photoshop things, like your instrument maybe like onto a dinosaur or something. So there's ChemRex, there's also the ChemDestroyer, pretty apropos, laser. And so, yeah, this one. The French were so confused. Why would people think our instrument could hurt cats? No, and like you try to explain this. I'm like, I don't even know how to explain this. There was a cultural moment there. So you can eat. This is a really fun job. I feel like I've got the greatest job in the world. So here's just a traverse map of where we've gone and where we're headed. So we've gone now 10 kilometers in 3 years, so not that fast, but that's pretty speedy as rovers go. Today is Sol 983, so we've been on Mars for 983 Martian days. So we started here, it's our landing site. We kind of tooled over here and drove down here. These are just waypoints where we stopped and did some science. And we are just past the humorously named Pahrump Hills, where we spent 50 sols. So we're going to zoom in here to this area. I'm going to show you now where we are right now. So this is this area. We drove down this pass called Artist Drive. And so we're right about, this is 976, so we're a little bit farther away, but we're right here. We haven't gone out of this depression yet. So I'm going to show you now a picture, which I really think is so beautiful. They just got these data down. So on 957, Sol 957, the mass cam took a panorama looking over here. So I'm going to show you an image, and you're going to see Jocko Butte, and you're going to see Apikuni Mountain and Logan Pass. So keep this in mind. So you can see now we're looking, again, toward this butte, so that's what it looks like. And then there's the mountain here, Apikuni Mountain, and then Logan Pass, where we're actually going to leave eventually. And this is actually only one part of this huge panorama. We have such beautiful images, And doesn't this sort of seem like New Mexico, right? Doesn't this seem like someplace that you could go for a hike? That's something I really love about Mars. So you might wonder, actually, why do we have these names? And who gets to name these things? Who thought of Apicuni Mountain, right? So it turns out that we name all of our features after real features from the Earth. So we have quadrangles that the USGS makes for the United States. In fact, we have these for all over the world that shows a particular area. And so we divided up Gale Crater into quadrangles that are similar size, and then we named them after, we assigned each of these quadrangles a quad on Earth. And so any feature that was in that quad on Earth, we can name something on Mars, which actually leads to some really hilarious things. Like there's a rock called Jum Jum, because Australia has a lot of fascinating names. Right now we're in the Arleigh Quad, which is a Montana quad. So if you're from Montana, you might be familiar with the Logan Pass and Apicuni Mountain. So that's where we get our names. So that's where we're headed. This is where we're going. So as we move on, we're just moving up the mountain in that direction, sort of this way, slowly and surely. So another future thing that we're doing, so we're still doing ChemCam on Curiosity, but we actually our team here at Lanza was just selected for another instrument on the upcoming Mars 2020 rover. So it's not named yet, but we'll be launching in 2020. So we're actually building another instrument that's called SuperCam, because it will have increased capabilities from ChemCam. It's going to be both a LIBS instrument, so it's the chemistry laser information. It's also going to have a Raman instrument. It's combined LIBS Raman. So we can actually get chemistry from the LIBS, and we can get mineralogy, so the structure of the molecules from the Raman. And so with those two pieces of information, you can uniquely identify a material, because with chemistry you get part of the story, and with mineralogy you get part of the story, but with those two pieces of information you actually get the complete story. So that's upcoming, and that's something we've already started working on here. This will also be made in New Mexico. And this rover has a different mission, so it's actually going to be looking for biosignatures. So we're not just looking for habitability, environments in which life could exist. We're actually looking for traces of life and materials that life could have used. So that's a really exciting mission, so stay tuned. And I'm gonna leave you with this totally real picture of ChemCam in action on Mars. That's what we're doing. Vaporizing things. So with that, I'll take any questions you might have.
Any questions?
Oh.
So how long do you expect this Curiosity to be operational, and are any of the other rovers that are out there still sending back images, or are they also operational still?
Yeah, great question. So we're not supposed to make any promises, right? We have to tell you that the rover could die at any moment. However, I think our track record is pretty good. Like the rover is operating really well. I think we have a lot of life left in us. We've passed the nominal mission. It's supposed to be 2 Earth years, so we've already passed that by 50%. And so I think we have a long way to go, which is exciting. So there are other rovers on the surface that are still operating. So the twin rovers, Spirit and Opportunity, were operating for years. They were only supposed to last for 90 days, so 3 months, and so that was in 2004. Opportunity is still going. It is still taking data. It's still bringing images. It's actually still doing a lot of really important science. Unfortunately, Spirit did not wake up after the last Martian winter, but it had outlived, her lifetime, her expected lifetime, by something like 11 years or something. So really, I think we have that's an incredible mission. So we shouldn't feel bad.
I have 2 questions. One is, you talked about the wind. Could you explore that a little bit more? And the other is, how do you relate to the television setup that's on in the shopping mall down here?
Sure, yeah. So see, the wind on Mars is the dominant surface process, because they don't have a very strong water cycle like we do, where there's rain and there's oceans. The wind is the most active thing on the Martian surface, except for that methane. I don't know where that's coming from, but that's what's really shaping it. So the wind actually it's not strong in the way that we would imagine it, because there's not a lot of atmospheric pressure. So if at sea level we're at 1 bar pressure, Mars is at 6 millibar, so 6/1000th. So it doesn't exert the same amount of pressure, so it can't carry heavy particles, but it can still carry light particles and scour rocks. And so that's how we have these sharp, pointy rocks, because you leave sharp, pointy rocks out in the surface in the wind for millions of years, and they get really sharp. And you have a lot of dunes that are very active. So that's something that we can see happening. And there's these global cycles. We have every 2 Mars years or so, there's these global dust storms, like a giant global haboob. And we actually cannot observe the surface at that time from either the spacecrafts or our in situ instruments, because we have to shut down, because sand is not good for your optics, turns out. So I know both Spirit and Opportunity definitely lived through some of those dust storms. I will go over here. Great. I have a lot of microphones on. I'm not sure which ones are doing what. So we actually, maybe your other question was how is this mission related to that awesome views from Mars? Those are all the publicly released images. So I'm not sure actually who's updating it, but it does get updated. And so those are images that come down. Our data are, the images are actually released immediately. So you can actually go to, those come from the websites mars.jpl.nasa.gov, and it gets updated almost every day with new pictures. So that's where those images are coming from. Hi.
Any controversy?
Controversy.
Any controversy in using plutonium to power the vehicle?
For me, not at all. I mean, that's exactly the right tool for the job, right? I mean, we couldn't have the rover without it.
But I'm wondering any controversy.
I mean, people.
From unlearned people.
Well, okay, yeah. So the questions that I typically get, yeah. The questions that, so when we launched the rover, we actually had to we had to be much further back than you might imagine. I'm trying to remember if it's something like 6 miles or something. And that's just because if the rover were to explode, which we were terrified of, we wanted to make sure that the plutonium would not hit people. There's very low risk in that, though. That's just the metal would just fall into the ocean. So it wouldn't really.
So I guess I would add on to that the fear of it crashing on Mars, and then it being, I'm very naive in any of this, but the Mars being contaminated with plutonium.
Then the question really is, people always ask me, like, you just leave your rovers there, like trash? And I mean, what does trash mean on a planet without inhabitants, as far as we know, right? I'm not really sure there's that's all that meaningful, right? I mean, we do leave everything that we've ever sent to Mars, it's still there. Plutonium and all of our rovers have had plutonium. In fact, many spacecraft have to have plutonium. It keeps it nice and warm. It's cold in space, and it's still cold on Mars. So it's still there, yeah.
We'll see what a secondary designer says about it.
Yeah.
I just wanted to ask on the 2020 mission, are you going to have stronger wheels?
Yeah. Yes, JBL is working on that right now. I'm not sure what they are going to decide on. I would guess that they would use titanium. Remember, these wheels are really big. Try to mill a piece of titanium this big. I mean, that's a lot of titanium. But if we need it, then we need it. We're going to use the same chassis as Curiosity, so we have the same rocker bogie system, which is a good system, but has that, it really puts a lot of pressure on the front wheels. So I think the only thing we can do then is strengthen the wheels, or go to a sand pit or something. And we haven't decided where we want to go yet, so we're not totally sure, what the material is like. So that decision is not going to be made probably for several years yet.
So what sort of languages do you use for the software? And do you just send commands to the software, or can you reprogram the software?
Yeah, I can't. The platform was something that was so obscure that I had not heard of it, and every time I asked, then I just forgot it, and it was terrible. But I was like, "What are we working in? What are we working in?" So I'm not really sure what the platform is, but it's actually we have a package called MSlice, MSLICE, and I'm not sure what the IC is, but it's the interface command something, whatever. But it's a software package that we use to build our commands. So we have a syntax that is for spacecraft commands. And so we know what parameters we need to change to do certain things for our instrument. And so that's something that we do as an instrument, and then we are responsible for delivering that to JPL. So the scientists get to say, we want to do this experiment, and we have to say, okay, now we build that command. So I can set, here's like the motor position I want for the focus. That's the kind of the things that we are commanding. And they all get bundled together by JPL and then sent to the Deep Space Network and then sent to our orbiting spacecraft around Mars and then sent to the rover. It's like this whole relay. And I think there's like, yeah, there's one person at JPL who does this. And he actually got into a minor car accident one morning and like we didn't have uplink. He was fine, but we did not uplink, that's all. I know, right? I'm like, we should just like chain him to the desk.
And there's a landing site, it's called Bradbury, and I have to ask which Bradbury?
Ray Bradbury, yeah. Yes. Very Los Alamos question. But Ray Bradbury was a real friend of JPL and was really involved, you know, and he's an incredible writer and obviously loved Mars a lot. And so he actually passed away right around the time that we landed. And so we asked the mission, even though it's not part of the quad that we landed in, you know, we asked if we could name this area in his honor, and they said yes.
Any other questions? All right, let's see if Dr. Lanza.
Thank you.